Hello and welcome back to another evening of Rust. We're going to continue with tic-tac-toe today and see where we go. We made it to the Gold League. We'll see that later. We kind of suspected it last time. We were kind of in the top amount there, 20 to 30, so I don't know where we sit now, but we'll find out. Let's start the show as we always do with a Clash of Code, where sometimes I do well and sometimes I don't. And it looks like chat's working today. We had a bit of your chat last time. Well, apparently I missed half the chat, but it's totally focused, but all alone without the chat. It's so sad. So tonight we're going to clean up the strategy code a little bit. We're going to think about how we do random, because right now random it could be faster, but it's not going to make a huge difference in how much we can get. We get another 10% iterations if we change that. We're going to create random strategies that we can plug in. What we're going to work towards is doing a setup even more correctly here, so we can pit strategies against themselves locally. And we had a suggestion from last time. What if we take a kind of a stepwise strategy that instead of trying to play the whole board, what if at every single move we have, we just play the local game? And we take the up move for the local game, and that means our iterations don't have to be so high because we don't have to cover as much. In particular, let's check that out. How many iterations would we have to cover at most? It's like factorial 9, which is still quite a bit. 362,000 at worst, but in most cases, when it's that filled, it's not a big problem. The first turn's gone. They made the gold boss insane, only top 50. Okay, do you mean the silver boss? I don't think there is a gold boss yet. So we're going to probably have factorial 8 or factorial 7 even. Because in the first, so 5,000 iterations is something we can do. Remember, we don't even have, this isn't the full game, this is a small game, so we'll probably do that many iterations. We'll see what we can do. Let's go check out where we are in the coding game. Is it really that hard, the silver boss? Just want to see where we are. Wow, are we in tic-tac-toe? We're at 40 seconds, so a lot of people pulled ahead of us. And we're up there in Gold League, and we're going to get better than that. Down to 42nd place isn't so bad, it's right at the bottom. As much as that seems like we're low, it gives us a good chance to actually measure our strategy. So we're hoping in there we have a good range. So we see 34 down to, oh, it drops fast, and we have a pretty good range down. Wow! That range is pretty deep, 18. So 18, 19. We have a lot of options to actually get up in the score here, so we should be okay. Get us some bonus, but we're not. We're just going to try one new strategy today. Oh, this one should be starting. Oh no, fastest mode. What do we have to do? The point is exactly between two other points. You're given the coordinates wired a blind line segment. The midpoint of this line segment is target points. Be careful which line segment coordinates line to the second point. Okay, I've done this one like a million times. But what do we have to write out? Okay, so what do we have is let x equal x1. Oh shit, this stuff has to be f64. This is slowing me down. 64, f64, f64. x1 plus x2 divided by 2f64. Let y equal y, I can't type fast enough, plus y2 divided by 2f64. Then we're going to have errors, and we want to put two numbers here, x comma y, and let's test this out. Let's just submit this and see if hope it works. That was pretty risky. Yes! We won! 58 seconds! Sorry, Petros. 2 seconds faster because I took the risk to press submit without testing it. Okay, finding the middle point of a line or doing lerping and stuff is something I do so much that code, that type of stuff, is just sitting in the front of my head. I mean, but that's a good one for fast mode. I mean, we could have done it faster, except I had to type the F stuff all around. And C++, oh, C++ has the same problem. But he probably did float or had float. I don't know what it is, but okay. Exact same thing. You see, even the exact same variable names, X and Y, and We beat them just by a tiny little bit, and so that's good. I'm very happy with that. That gives us a good score. That gives us a good start. This clash was exciting because that was close. Difficulty. This one's kind of easy. Statement. Yeah, that was clear, not very clear. And what else do we have? What else do the people have? Zero. Somebody submitted with 0%. They just gave up, or that's weird. Look how close this was here. 104, 113. I'm happy. I don't think I've ever gotten first on one that fast before. All right, well that's good. We have that out of the way. So let's move on to tic-tac-toe. And I guess we're being streamed over at Ferris's stream, which is great, perfect timing. So we get all his viewers here. All right. All right, we got to do this. Got to switch this off. I just turned this off for a second. Okay, use the previous selected file, upload file to IDE. There we go. So we're at this rank. We did gold, and from last time we got pushed up into gold. We're right at the bottom of gold. We kind of suspected we might be. Reknakas, this Foxy plugin here is a proxy manager. In case you want to do proxying through various servers to not have your traffic all tracked by the same place. And today I was playing a bit more. I got the SSL set up again, and that's in the French server, but I'm afraid to turn that on right now because the response time is a bit low sometimes. And so the German one usually works, but if I have that on, then I don't have the pattern, so I'm not excluding the local host, and I need to have local host. And it's the one problem I have with Firefox is Foxy proxies, I don't have like a global whitelist saying regardless of what I'm doing, please don't use it on this one. You either have to use all of them or none of them. I wish I could change that, but I can't. So I turn it off right now. We're not using any other sites. We should be okay. I don't think they're tracking us. Well, they are. We're doing everything publicly. So this Fox proxy is quite nice. And I use TorGuard as the proxy servers. And I just think it's good. I encourage people to do it. Even if you can't use it all the time, it's good to just proxy as much as you can to hide as much traffic as you can from unauthorized monitoring and even authorized monitoring. People don't need to know everything we do. Okay. So our tic-tac-toe. Why is this... oh, I was just joking about something here. Let's get rid of that. Oh, wait, this is my joke about... This is after the Uber crash. We're debating whether the car should have seen it. I don't know if anybody's seen the video of the Uber car crash. and from the video, it looks like, you know, maybe a human driver could not have stopped. The problem is these cars are equipped with stuff like radar and laser detection. And I would hope infrared. I don't know if this one had infrared, but it definitely had radar. So that car should have definitely seen that person in the night. Now, I don't know how they're going to judge it because it's like, well... Even though a car could do better than a human, does it have to? I mean, I would still hope to see him on the road because it's still better than that. But, and this is my joke here, what do you do if there's an unavoidable crash? And I wrote it in Rust because that's what I had. And we're going to sort the targets by net worth and drive towards the one with the minimum net worth. This is the dystopic future of the automated cars. We'll just ignore that. We'll save that. We'll go back to tic-tac-toe for now. So this is RLS. It works once, and then I compile something and it breaks. You know, it might be a great plugin, but it has problems. And so what I wanted to do today is we look at entries. So if you haven't seen the show before, my strategy basically is I have a module, and I'm using a couple tools to pack it all together and submit it up so the site only submits one file. But I have this basic entry code, and the entry code is what actually handles the input from the game. So it reads the standard in, and let me close this a bit. It reads the standard in, sets up the game, sets up the move, and the core of our logic is way down here, called get best move. This is the only really interesting part of entry right now. The rest is just sort of boilerplate to interact with the game. Get best move is the one that invokes a strategy, and the get best move strategy is right here, and it has a state. Now, what was I thinking of doing? Let me show what the problem was last time. Is we created a function called getGlobalRNG, which is a XOR shift RNG, which is still slower than I'd want. I don't think I addressed this one now, because even if we increase the number of iterations, it may not help us enough, because I'm looking at those other guys. I mean, if I look at the other guys in the chart, we're down to 42. These guys are clearly doing something entirely differently. Even if I could double the number of iterations we get, we're not going to make it up to like 10th. It's just not going to happen. So we're looking for different strategies now. And I'm guessing we're going to have to go into the heuristic strategy. What somebody on Twitter recommended is something called fractal AI. I have no idea what that is. We might check that out. But the first bit here is to maybe look at the strategy and clean it up a bit. Is that I'm undecided on, should these strategies be objects, types, or just functions? Right now they're just functions. They take a board, a player, and a size. And I think it'd be better to make them functions, because then we can split them off into their own files so they're clear what we're doing. But then it should also be possible to give them parameters to tune them a bit more, because right now we're just kind of hard coding it. And if we play them locally, we're going to want to have something to better track what's going on. So there's something outside my window making lots of light. Ghosts. It must be the ghosts. And, well, Ragnakas, it's easy to say that they're doing min-max, but the thing is you have to be able to evaluate the things. And so if you do min-max, it implies something more. You can't just do min-max without knowing the position of a board. And like we're not doing the min-max aspect yet. We could, but we don't go very deep. And we could go deeper, but we tried last time heuristics of the board, and we actually do have board heuristics. We score the board, and that's one of the big issues that we have, is we have this scoring function. Our scoring function is called predict state. And it's very simple. It's predict state. It says, given the current state of the board, who's estimated to win? And we actually submitted this, and this was actually doing better. This with the short depth was doing just as good as a deeper depth without predicting the state. And that implies something really helpful here. And we'll get to that, which is really helpful, is that this predict state, though we don't know how to set up the neural net to play the whole game, something like predict state has some very fixed sort of rules in it that if we wanted to, this is the thing that we could do. If we played it locally millions of times, we might be able to hand tune, or not hand tune, we might be able to tune the values of predicting state. Because if you had a perfect prediction score, then you don't need to do many iterations. You just need to do a couple of them. And then you could actually do like 4 or 5 levels and just breadth first, 5 levels deep, with the min-max based on the scoring, and say, all right, this is what we do each level. But since we don't have a perfect prediction, we have to go fairly deep and get a better sampling in the Monte Carlo to help us with what the state is. But we're going to try a heuristic approach first. And we're going to clean up the strategies. So how do we want to clean up the strategies first? Let's do the... Now I'm tempted to say who's the player, who's the board state each time. And again, we have to watch in Rust here. You can't have multiple links to state. That would be a bit of a problem, so we're not going to do that. We're going to make a function interface here. And I forgot how to do the interfaces. I gotta look at the other code we did once before. That was, where do we do the interfaces? That was in Borders of the Galaxy, I think. In strategy. We do something like this, public trait strategy, get turn. And let's close this off and put this up at the top. So we have a strategy, and the state is going to be, we're going to take exactly this. We're going to leave the player as, we're going to make that a state variable, or I'm actually not sure. I'm wondering if this should actually be a variable of the state itself, mainly because the state may need to track for this player who will be concerned with it. It can't randomly switch between the players, so if it's storing any state, it might need to know. So we're going to take this off and just do this. So, and it doesn't return a game, it returns a usize, and this is the encoded move. Usize refers to the big grid, small grid combination, the index, cell index in each of those, and we haven't bothered wrapping this up to a state. A simple tuple is fine. We're pretty sure we know what it does here. So now we have this trait, and now we can implement it in various things. So now we could say, let's do a trait. Let's do pub struct strat. And what is this one called? This one is, what is this one doing? This one is doing, this is doing the Monte Carlo sampling. Well, it's also doing predict state, I think. Where's it doing predict in here? Predict state, play to end, predict state, predict state, predict state. Okay. So let's call this one Monte Carlo predict. And it's going to need the player, this is a use size. And this is the one thing I don't like about Rust, is to implement a trait is we have no force, but we have to do multiple implementations. You can't just sort of combine it together. So now we're going to actually have to implement something like this. And say function, public function, or public function new. And it's going to take player, use size, and it's going to return self. And what will this return? This will return strat Monte Carlo predict player. And now we have to do the same thing, implement strat, what would we call it? Strategy for strat Monte Carlo predict. And I say this is I can understand why you would do this in Rust, the logic behind it. In some cases it's advantageous to have multiple implementations, but here it's kind of a lot of duplication. I mean, we have to duplicate this, and this kind of separates it out more than we want. So this is get turn. Then we have one function called get turn, and this actually becomes the best move. So let's take this one up. Let's put this back on the strategy. Let's keep some documentation here. Why not? Get turn state. Get turn for the player of this strategy. And these both have to be passed in, the state and the force board index. And they're both read-only. We don't have to modify the state. And the board index, as I said, if we have a forced move saying where in the big board we have to play. So get best move is down here. We'll throw this up here. Put this in line. And I don't even, we check player here. Player, self.player. And self.player. That should be good. Ah, this stupid pop-up. Get best move score. Now it's hard to say if this should be also part of that strategy. It makes sense. Let's just throw it in there. It's I don't know if we have to make public function. This is the part I don't quite like about Rust here. So I'm going to do this, and now you have the function. Well, where does this go? This goes in the base class, I guess. And I don't know. I don't know for sure. I think we're just going to leave it out here. We're just going to say get best move score. Hard to say. That could be a generic function. Now, get next move is another strategy we can do. We're probably not going to ever use it again, but let's just code it up there just so it's clear. I'm going to duplicate this all again. We could throw it off into its own file then, although that makes it really annoying. Every time we add a file in Rust, we have to go add it to lib and then have to import it. I also find that less than ideal, the amount of importing you have to do just to split off files. It makes it a little less convenient to split them off. Not marked strat next. We'll just call it a strat next free. Now the reason why I'm splitting off these strategies is because I want to create a plugin system where we can quickly swap things out in the local player and test other strategies without having to go through and manually code everything all the time. Strat next free. And you notice here this use size here, This repetition here also bugs me because you don't have inheritance here. You can't actually make a base class that they all say a player, so you're actually going to end up duplicating this player between all of them. If somebody knows some way that we do that, I don't know. So we're just going to do it right now. We're just going to duplicate this code. So this code is going to be not highly redundant, but somewhat redundant because we do not have base classes or abstract classes. Okay. So this one doesn't even use a player, to be honest. Now, the reason why I'm going to keep it with the player here, though, is just because... Now, I wonder if this actually be part of the strategy, part of the trait, the creation based on a player. And no, it's kind of pointless because they're all going to have their independent strategies as well, but start next free probably doesn't need the player. We'll just leave it there for now. Yeah, no, let's just get rid of it. Doesn't need it, so let's just do that. Alright, and once more we have strat random. Random is the most generic one, and it also doesn't need a player, so let's probably reduce simplification. Strat random. Random just takes a random move. These are the degenerate strategies. They do not work very well, but they might be good just for a basis there. This probably, I don't know what needs to be pub or not. It's really weird considering they make the struct pub, but the implementation not, but the function inside of pub. I see inconsistency here, but I'll just do the way they want it. Random move. Okay, and what we're going to have to do now is, you notice RLS doesn't do anything anymore. This is the plugin for Visual Code for Rust. And it should detect errors now because the functions we call no longer exist. But what we can do now is we're going to create the strategy up here, let. And we're going to do... To be honest, these should be mutable strategies. They should be a get, turn, and mut self. Not just end self. Because the strategy has to have the option to update itself. It changes as stuff is done. Strat equals, what do we want to say? We want to say strat, what was one we're using right now? That is strat Monte Carlo predict. Predict, and we have an issue now. Crap, I'm going to do this correctly here. We have to create it down here because we have to set the player index. State.player. Which kind of puts us in a weird place. We'd prefer to have the strategy initialized up here, but we don't want to set the player, and I don't want to create like an init function, but maybe we should create an init function. It's just really hard to say where we should do this because putting the creation down here is going to be confusing when we want to change it. But this is just for the main game. In our test games where we change it the most, we don't have, we can put it wherever we want. And because we don't intend on changing this so much, it's not so bad. So let's just leave it this way for now. All this stuff is irrelevant from the strategy. Now we have... Now this is kind of hard code to just take the fourth turn to start with. We'll come back and revisit that again. It's something the strategy should actually do. But would it actually know that? It should know that. What do they call it? Get turn. Get turn and state.board. We don't need the player anymore. Yeah, and I'm really thinking it should probably be inside the strategy. Because the state will know that it's the first turn. It can check how many things are there, but it might be costly. I don't know. Let's just leave this for now. Let's see if this actually builds. Cargo build. Clear in cargo build. We got errors. Get a random move. Yay! 30. Yeah, this is the play to end. They get random move because we stuck it down here. And this was the random move. We'll have to make this a helper function again. And so this one down here just becomes get random move state, force. So this is part of the aspect of min-maxing here. So when we play to the end, we don't consider what the other player would do. We just consider what we would do. But the thing is, if we have to consider what their best move is, it just complicates our problem a lot more. If we can't figure out what our best move is, I don't know what their best move is. It's that recursive relationship where you don't know what the best move is until you know what the best move is. So this is where the weirdness comes in. And to understand the Monte Carlo approach, if we could do millions of iterations, the Monte Carlo approach would work wonderfully. I mean, because millions of combinations would let us know, but as we saw last time, I'm getting like 1,000 combination. Not even thousands. In the initial states of the game, some things like 1,000. Nearing the end, I get tens of thousands. So nearing the end, we make a decent strategy, I think, but nearing the end is too late. I think the game is decided much earlier, and I think the final moves are kind of just like buying time. Okay, next for you might want to do that too. Okay, what was this? Did you mean... Yeah, I probably meant strat. 64. I meant strat. Did you mean strat next? Wow, I typed it wrong in both places. Strat next free. Woo, what else did I type wrong? Stir in every single case. It's probably because I copied and pasted it. So like I say, this having to go down here and not having anything embedded in the editor, I'm used to this, but not with this editor, because this editor, you know, the embedded console isn't that great. But the RLS, if it worked, would be better, but it just doesn't work, so there's nothing we can do about that. No method called get turn for state get turn. Oh, that's supposed to be strat, not state. Strategy get turn. Get random move in strategy. Where's this called? Get a random move. Call it again. It doesn't need to know the player to make a random move. All right, this is the case where it's going to kind of piss me off here, and so logically it can't detect the fact. Well, no. All right, so this is one of these errors that actually kind of annoys me in compilers. Use of possibly uninitialized strat is if you actually watch this code, there's absolutely no way it's uninitialized. edA-qa is the code. It's this RLS plugin. It just stopped working. Once we went to this project setup, it just stopped working. It worked on individual files, but then we went to the projects and it just stopped working. And the problems output would show the simple things and you just click on them, but it just stopped working. We don't know how to get it working again. And I've reinstalled it. I did the update. I've opened a project. I closed the project. I just do not know. It just doesn't work. I don't think it's Visual Code's problem. It's this Rust plugin, Rust language plugin that's just not working. And if anybody has any ideas on how to fix it, I'd be happy to try and fix it. But our Rust project setup is extremely basic. I actually based it on like a recommended default. So if we have these files here, we have the source, we have the target, this is the output, we have the test directory. Inside source, we have the lib directory, we have the bin subdirectory where the binaries go. The only difference is in the main file, we have a single file, which everything outputs to, and a special main file to work around an issue in the building plugin. But it's fairly standard, and RLS just looks at it and goes, I don't know what to do. So we're stuck with compiling on the command line, and Cargo knows what to do. And I'm surprised that RLS just isn't using like some of the standard output, because the standard Cargo here works, so I don't know. We also have it compiling twice, though. I'd really like to know. It'd be really helpful, because it was a lot faster when we could just double click in here, and I don't know why it doesn't work. Alright, so let me explain again this error about here saying that strat could be used possibly uninitialized. The compiler's actually wrong here. And I know Rust is a safe language, and I can understand why it gets away with this. The issue here is that if you actually follow this flow code, and it's because of this true here, turn true, if you follow it logically, first turn true here is always true, and so strat is always initialized. So we actually know for sure that strat is always initialized, but the compiler doesn't make this level of analysis. The compiler sees, hey, look, this looks to be immutable, and so it gets to this thing here and says, well, this may or may not run. And that's totally legitimate. This may or may not run, and it's in a loop. And then it gets down to strat, and it says, well, you know, you haven't initialized strat yet, because if this was false, you wouldn't have initialization. So legitimately, it's kind of legitimate. So what we can do, just to keep it happy, is just say like this, strat random new, and just say it's never used. And this will keep the compiler happy. And, oh, we have to give it a force type then, so this has to be a strategy then. And this is probably going to piss us off with this boxing nonsense. This boxing shit again. How do we do the boxing crap? If you can't tell, I'm not a fan of this boxing approach. Box. We have to have a box. Traits are not interfaces. Traits are just stuff that has to implement it. And that means you can't actually say something is of type trait, because that doesn't give enough details. I totally understand. I know why they require this box stuff. It's just annoying. Doesn't change the fact. It's one of those horrible lessons of language design. Doesn't matter how correct something is. If it's annoying, it remains annoying. It's the same with API design. I had that a lot when working with Fuse stuff, is that you have APIs that, even though are correct, people just find it like, blah. So you end up making an API that's more friendly, but it's less correct, and then you have the problem of, well, how do I deal with the people that want to do it correctly then? Whereas Rust seems to be going the direction of, hey, let's just do it correctly at the expense of people looking at it going, blah. So you have that option. It's a horrible option when doing design of languages and APIs. You can't please everybody. And if you're used to an object-oriented, if you're used to interfaces in other languages, this boxing stuff is kind of annoying. But I can understand why they do it. Alright, now what do we have here? New player. Now we have some stuff. We're going to go through and fix all of these warnings, because we're clean coders and we agree with all of these warnings. Strategy. Unused variable score. Fine. The unused variable stuff is kind of annoying, but you can understand why, in general, you want to say, like, look, you don't use score. It's like, well, that you should use it. But we print it out here, so every time you come in and out of line, you have to deal with that. But in general, I am in favor of unused warnings on that. Free doesn't take player. It's good. We want to make it not take that. And, well, that one here, I don't know. I'm not a fan of these naming conventions, and Rust has a lot of inconsistent naming conventions. It's like there was a bunch of people that got together and said, what naming convention can we use, and they couldn't agree, so they just used all of them. There's some uppercase stuff, there's some lowercase, there's some mixed case, there's camel case, and now we have all uppercase, but this applies to globals and to constants, so not just like constants, but to globals, and for me it's just like, it's not helpful. And the reason why I don't like it is because if you're using something called global RNG, what do you care if what it is? I mean, it breaks the abstract pattern if you have these really strict naming conventions. The same thing that bugged me in Python as well, the very strict naming conventions between types and instances, is that if you have a language that can take a type as a high-level variable, the distinction is completely lost. And because it's unclear of whether this should be a type or a function, and we have traits. So, I mean, I'm not a huge fan of these really strict naming conventions, but we're going to follow them, just get rid of these errors. All right, so play we have to fix. We know that. Play, these are all play. Good, let's go over to play then. So play is the one we want to look at. We have these plays, and we have the result for the two players. Play to win s.board player 0. And we'll figure that one out. We're going to give it a strategy. What does play to win do? All right, so play to win is going to have to take two strategies. Let mut strat 0. And this is the player we want to actually win. So we're going to say strategy Monte Carlo predict new 0. Let mut strat 1. And the other player is going to play at random. Monte Carlo, no, not strat random new. And we're going to give it this one. This is play steps. We'll make this play random steps. Set up the board randomly. Note we started at 0 though here for testing something, but this sets up a random board. And play to win is going to have and mut strat 0 and mut strat 1. And so we can plug in different ones to test. And where is play to win? Play to win is right here. Player 0 is a and mut strategy. And this is where it might be confusing if you're new to Rust. Well, why can we just use strategy here and we had to use a box in the main code? And it's because here it doesn't own this type. It's just borrowing this. It's going to be borrowing the strategy. So in terms of compiler development, it's totally safe to give it a pointer to whatever the strategy implementation is, because it doesn't have to borrow it, it doesn't have to manage the lifetime of it, and it doesn't have to do anything with it. So you don't have to box that one up. In the main code, it's because it has to do with lifetime, like the entry, that's why it needs the box. What happens in languages like C++ with shared pointers or virtual pointers, and Java and maybe C#, I don't know so clearly those ones, is when you have a pointer to an interface, it's actually more of a compound pointer. How exactly it stores it different is that it has a pointer to the specific interface you want, as well as having a pointer to the outside object. So if it takes a sub-object, and in C++, that's actually done inside the memory of the object itself, the interfaces have like a this pointer. All of them have a this pointer, which is an offset from the current pointer saying, where is the main object? So if you do have to cast and stuff, it knows how to get back. In Java and C#, I don't know if it's actually storing it that way. The alternative is whenever you have an interface pointers, you actually pass around 2 pointers. That's another option. You point to the interface and to the main object. I don't know which option those ones use. Those are the 2 basic approaches. If there's another one, I just don't know about it. And so here it's safe to use the animate strategy because we don't have to deal with lifetime. And so now we just do player 0, we do player 0 dot get turn, and it takes the state and the force. Else we're going to do player 1 dot get turn, and it's going to take the state, whoops, and the force move. Getting ready to clean this formatting up. Should these be in an array instead? Yeah, quite possibly. Then you could avoid the if statement. But we only have 2. It's always tempting. When you only have 2 stuff, it's always like it's easy enough to let laziness set in and say like, oh, it's just one if condition. And then we have to change this. And if you pass an array here, maybe. I'm not my biggest concern at the moment. Let's get it running and then think about that. If somebody's mortally bothered by that if statement, we can change it. Yeah, okay, state. Oops, I did something weird. We're still getting errors. Use of undeclared type or module strategy Monte Carlo predict. Okay. Oh, because it's just strat. I think that's what it is, just strat. Where did I do that? 81. Strat. $33. Play to win. Oh shit, so it needs the actual current player as well. Current player, so it still needs that use size. Current player. We don't need to say use size, just do that. And then play to win needs to say it's player 0. Get random move, number 23. Does it require a player? Play random steps. Alright, so we cargo build and we do target slash debug slash play, and that'll play a game. And there's some of our benchmarking output there. 0 wins, which is expected. Get states nice and fast, globals nice and fast. Good. So we're in exactly the same position we were before. Get status, get commit, separate out strategy trait. Now, if you notice, I never push anything in Git because I'm not publishing this on GitHub or anything. I have been requested not to publish strategies for the games where we're probably going to get to gold and stuff, which is going to be all of them. I mean, I don't think we stop below gold on any of them. And if we get to legendary stuff where we don't publish strategies, I do have a separate backup strategy, obviously, for my code. I don't just keep it on my local machine. But it's not in GitHub or anything. And the reason they don't want us uploading it is not because you don't want people learning from it. It's mainly because if you have a site like this and somebody has public code around that does like really well, it's easy enough to just copy and paste it, and then everybody can do that level. A bunch of idiots can come by and just copy it and just don't put any effort into it and get a very high rank on the site. Thanks, Rick Knockus, for the reminder. Yes, there is one where we're stuck in silver. Mean Max. Okay, yes. So we could easily post our code for life in Mean Max code. And Mean Max, that was one of the earlier ones I did. Wasn't that like one of the first one where we decided, hey, this is far enough. I don't know what I'm doing. I better try again. Code for Life, we took the wrong approach. And when we get back to it, is Code for Life, we took a scoring approach. And that was like basically a failure. The scoring approach for Code for Life, because it was too complex to score correctly. Now, we could have partially scored it. We should have done partial scoring. And so if we go back to Code for Life, I will go back and just redo it with a heuristics-based approach instead. We won't redo everything. We can take the existing state logic and reuse that. But we'll actually use a heuristics approach instead, and we would have done a lot better. Heuristics is exactly what we used in the Botters of the Galaxy competition. In Botters of the Galaxy, we got really high. We got the 63rd in the ladder, which is really quite good, and that was just all hand-coded if else, if else, if else, if else, if else, if else, like an expert system that's been manually trained. But for tic-tac-toe, we're going to go this, we're not even doing scoring initially, we're doing just evaluation. So the initial approach for tic-tac-toe, which is even recommended by the system, is Monte Carlo tree sampling, which is a terrible idea if you can't do millions of iterations, which you can't. You can do thousands at best, which is not enough, because Monte Carlo has that thing that it kind of sucks if you can't do thousands of iterations. The last time I did Monte Carlo was for poker, and I was actually doing, like, and poker doesn't require as many evaluations, because if you're playing like Texas Hold'em, there's only 3 more cards to come up in the game. So if you have, like, after the flop, you have like those 3 more cards, and there's a lot fewer things you have to evaluate, but the poker code I had evaluated really fast. I actually didn't flash. The flash code is actually evaluating quite fast for being a high-level language like that. But they're like stupidly hand-optimized. And the server code, I also had a server one, which is based on an open poker library, and they can do hundreds of thousands. And a game like Texas Hold'em, that was more than sufficient to get an idea of the outcome. Also because the scoring is super simple to do. It's like a simple based rank scoring. Like when you have one particular scoring hand, poker hand, you know it's global rank. It's not like you have to guess at the rank. You can say, well, you know, a full house of these 2 cards fits exactly in this place in the ladder. It's an absolute score of how good that is, which made it ideal for Monte Carlo plus scoring, which is no problem. But for tic-tac-toe, you have to play right to the end, and you have to know the opponent, and there's so many variations that makes it a lot harder. But that's what we did. And now we're not stuck with it. We're going to do a heuristics approach to that. That's the idea today. We do the heuristics. Do we upload this? Let's check and see if we actually have the same code uploaded. And rank 42, that's where we are. This is the exact code we did. We just resubmitted this. I just want to make sure it keeps working. Obviously against the default AI we're winning because we have no idea what the default AI is doing. Okay. So the whole purpose of this refactoring exercise was, now we want to create a new strategy. And I'm going to take out some of the benchmarking stuff first of all, ePrint, just to get cleaner outputs. That was the only one number of iterations. We'll get back to that because we're not thinking that's the biggest deal now. Do we want to create another file? I'm not going to create another strategy file for now. What I want to do now is going to create the strategy that was recommended on the show last time, or to experiment. Let's just call it strat local. And we need to know the player in this one. Player is use size, because we need to evaluate who wins. You know, so that's about the strat ran and the strat next strategies. They don't even need to know who wins. They do absolutely nothing. They just take the next thing. Strat local. Actually, let me show something first. To get an idea of how this is going to work, how you pit 2 strategies against each other. So this is one you have strat 1 is random new against Monte Carlo. So we can easily switch this out, and we can instead say, well, who wins if we take strat next to strat random? And this is the idea of doing local tests. We can check who wins these things. Next free it was. So you can check who wins between strategies locally. And we want to make the play multiple versions of the game. 0 wins, which is really kind of frightening. And this is how we got past the Wood League and the Bronze League, was the strat next free actually beats a random strategy. And next free basically is, well, not basic, it is on a board. On this board, it simply scans from the top left going down, well, which square is free? And let's take the first one that's free. And the reason it probably works is there is a bias to fill in values as opposed to random. It's a very slight bias, but it's enough to actually win. So you can see 0 always wins in this case. Oh, there was one random one that won. Oh, now just as I say that, just as I finish saying that, random always wins. And just as I finish saying that, it goes back to the strat next free. Which is okay. I mean, we have that, and we don't even need to do this perf checking anymore. Let's just get this cleaner. We really want to set up a play program that can do it 0 wins. So, this is going to be the issue that these strategies, they're going to need some kind of reset function as well, because we want to play a whole bunch of games in a loop with these. But I have no idea how to specify a generator. I know how to specify a generator without doing a lot of work. And I don't know how to do like templating in Rust. I guess it would work. No, we're going to have to create factories. But anyways, let's do the other strategy first and see how it behaves. So we'll just randomly do the loop on the ground for now on the code. What I want to do is in main, I want to code a loop that runs the strategy playing a whole bunch of times between the players so you can see who on average wins. With the random ones and next ones, it's very fast, but for the Monte Carlo predict, it's going to be slow because each move takes up to 100 milliseconds. So even running locally, you can't avoid that. It's just going to take 100 milliseconds. The best we can do is compile it in release mode and say only take 10 milliseconds to speed it up. But let's go back to writing the strategy instead. The next one, strat local. Strat local public function new, and this takes a player use size. Return self. Self player. This notation without something like this is like JavaScript syntax, where if you use a variable called player, this by default assigns it to a type called a name called player inside there. It's a nice shorthand and for this type of creation. Now we want to do implement strategy for strat local. Get turn and mut self. Now, dealing with this forced board index is going to be a bit complicated because all of them have to duplicate the basic logic. Basically, is there a force or not? What do I have to do next? What do I have to do next? This one's not so bad. We got to find the big board and the small board. So, what we wanted to do for this is give it a small board now, not a big board. We want a small board. What do I call this small board? Given a small board, what's the best move for the small board? So function get best small move, and this will be a board and small board. It needs to have the player now, because we need to know what player it's winning and what turn it is. And we don't need to know the board index. We just want to know the best small move for this board. Where do we want to play? We don't need brackets, I guess. Okay. And what this is saying is for a small board, don't consider the big strategy. Just take a small board. Wherever we are now on the small board, just pick the one that wins the best there. And here again, we can do we can do the Monte Carlo sampling for the best small move. And we're hoping here, and maybe we should do, this is the case that we might be able to get away with doing actually a complete depth search, assuming it's not too much. That was a calculation early in the show. For the very first move, we have 362,000 possibilities. which may or may not be enough, to be honest. So I'm not entirely sure how we'll do this yet, because the moment it gets down to the second move, we have 40,000 iterations, which I strongly suspect we can actually do fast enough. Now, we know in the main game I said we can only do 1,000. That's because the main game has a depth of 81, a search depth of 81 to complete the game, and it's more more complicated to calculate. For the mini game, there's a maximum depth of 9. That's the depth right here. And these are the same, and this is why I calculate the moves, so there's a lot fewer. And the moment you get down to 7, you can basically just calculate every single possible move. So maybe we should go on this approach, is to say, let's evaluate every single move, which one leads to victory, and we just count them all up. And there we can min-max it. There we can min-max it, because if any move the opponent takes leads to us losing, then we don't take that move. We just absolutely don't take that. So let's hope for the best that we can evaluate the complete board here. So get best small move. And here we have to do the splitting on the big board, small board again. Okay, which might be an issue here. Copy this basic setup. If we have none, we do next free. Let's get rid of that first of all. So which board do we want? We want match force. No, next time we just get the next one free. And we'll fix that one right away. I just want to get something working first. Board index cell just becomes SB. And we should probably do next random. Yeah, random move. Random free. Let's just do random free. So we take a random one. Well, we'll fix that later to actually use to get best small move. So give it a small board. Now we want to say, well, what is the best move on this small board? And we'll say small board move equals get best small move. And what do they call these boards? I keep forgetting. I haven't worked this in a while. So state dot small SBX. And I guess this is a reference to it. And for player, what player do we call this? Self.player. For this player, what is their best move on that? And we'll say SB move. And SB move is just a cell index. So now we have the depth here. We're going to have this depth. I'm going to start cloning this a bit. Now, our boards, our small boards, are tiny, so cloning doesn't cost anything whatsoever. And how do we set this up then? How do we set it up? At each level, I want to get the small move. What wins? Setting up these recurrences is always kind of annoying. The initial setup, once we get it set up, it's very clear what it's doing, but it's always hard to set up the initial tree scanning. It's a pain. It's easy to visualize what it does, but it's hard to translate to code. We're going to keep a score for each of the small boards, which is the best move, and count them up on the individual ones. And we did that somewhere else already, that same basic logic. Play to end state, not that. Right here, get best move score. We did something like this. Ah, yuck. For all the cells, give it a score. And I think we're going to have the same basic strategy here. So this was the Monte Carlo setup, get best score. Alright, I'm just thinking again. It's the same basic setup. Trying to avoid just copying and pasting, which I sometimes tend to do. For each cell, we want to evaluate the score of each cell. Well, let's just copy the bits here. Let's start from here. So the score, we have the number of cells. We really only need the score. We're not tracking anything more. So we're just going to track the score for each cell. How many points does it have? And we can get rid of this bit. Let's call it score. And the closed is to get closed mask. These are all the cells that are closed. So now we do for I in 0 dot board num cells. And for each of these, we're going to clone the state. CB equals board.clone. And CB dot set player linear I comma player. I think that was it. Let me check. The pop-up doesn't work either. That was part of RLS, so cell player. So we don't get the pop-up anymore either. Set player linear. But we can actually check the state if closed and 1i, we skip this one. So we don't have to evaluate the ones that are closed. This will be faster. So this player here, and this sets up the basic recursion. Now we want to go down and say who wins this board? How often do they win this board? And that'll be a score. We score that board, and the score is going to be the same basic thing. We're going to rock through the whole tree. And so score I equals... Do I have a play to end here? Play to end. Yeah, the play to end here is the one that does random moves. Not play to end. And the score to end. Score to end, this is going to be the clone board. And the other player. We need the other player. How do we get the other player? It should really be a function that does this. Public function next player. This costs us time in the main game. So I'm reluctant to do this because in debug mode, this costs us a lot of time. But let's play on the safe side, first of all, and not worry about that. Next player, player use size. It's use size. We can try this inline always and see if it helps. This is just player plus 1 mod 2. It just makes it a lot cleaner when... Where was I? Next player, not Bext player. Bext player is good too. I mean, Bext player, player. And then we have to sort them by the person with the highest score. And let's see if we can do this logic again. Now what we want to do is we want to return score.max by... First of all, we're going to do a iter on this. Then we're going to filter it, an item. I'm going to say, and we need to enumerate it. It's pretty wacky because we need to know the index. Inter filter is index comma item, and we don't need the item. We're going to return I equals 0. So only items that are not closed. And then we're going to do a max by key. We don't care about the index, but we care about the item. Item dot, just item. And we know this returns a value, otherwise we're just going to panic. If the game's done, I don't care. It's broken anyways. unwrap. Unwrap. All right. So this is the rusty syntax for how this works. I'll just do it this way. Iter converts this thing into something iterable. Vectors by default, whatever that is, or an array is not iterable. Enumerate converts it into the pair of index comma items, so we actually know the items of it. Filter says, that's the wrong line. Filter says only use these items. So index, we're only caring about the items where the board is not closed. Max by, because the value is going to be plus or minus, so we're not going to consider as negative ones. We could also simply remove the filter by putting a very low negative value here, but that's an optimization we'll do later. And max by key says, now take the value by key, given the key index and item, the one with the highest item score, so this is the max function, dot unwrap, because it's optional, because it has to deal with the case where filter iter returns an empty list. But we know it's not going to return an empty list at this point. If it does, we're going to allow it to panic. So now what we need is a score to end function. Score to end board and small board. Player use size. And this returns a score. What score equals 0? Now I'm trying to think of how to score this when a player wins. That entire branch is gone, because what happens if you have a board because you have to logic if there's like if there's like 5 spaces open on a board, but one of them leads to the player winning, that wins. They would never pick another one. So you don't want to just score all the possibilities. You really want to just score just that one. Because you're not going to be stupid. And scoring for this player. Score to end. No, we have to know for which player it's scoring as well. Interesting. Score. For this player and which turn it is. 4 player, current player use size. And this determines the score for that player. And how do we determine that score? Well, we set up the board first of all, and we're going to say if they've won or not. How do I do this now? Again, we're going to do closed again. We're going to do the exact same closed stuff again. Okay, for I in 0 board non-cells. Continue, there's nothing to do here. And these loops are going to be very similar. And this is always a case of choice. I always have a hard time merging the big loop into the small loop, and so I end up having 2 functions, and we'll have to check if it is actually possible. But see, the key difference here is that this one's trying to pick the best move, and this one's just trying to score it to the next move. But if we do the min-max, then each one of these should in turn called get best small move, which has to iterate through there. And, well, we'll figure that one out after. So basically get best small move, if you want to do this correctly with the min-max, is each iteration is going to call best small move again, but that would be really stupid, that would be really expensive, so instead we're just going to score it through. So it's not really a min-max strategy. We're just going to evaluate everything first of all without consideration for the best moves. It's not ideal, but let's see what happens. Let CB equals board.clone. We'll clone it again. CB.setPlayerLin I, player. We should actually check the game state here. Yeah, whatever. We should check the game state here. We have an issue that if this actually finishes the game off, it's winning. I don't know where to check that. We have a double first step. First player Len, and now we detect that. Match CB get state game result closed. This just becomes 0. Nobody wins there. Game result win player, or what should I say player. If PL equals player, then we return 1, else we return -1. So if the player is the one we're hoping for, then we get a +1 because they won the match, otherwise we don't. And again, this is where the logic comes in, though I have to really watch that. In the case of a win, this score should dominate. Right? If any one of these things here causes a game to win, should dominate score. And actually, we could do that quickly. We could actually do this. We could do a hard return here. So this is no longer a match get. We're going to do this and do score plus equals 0. Now the reason I'm doing this is because if we ever detect a win, this is a one-move win. The score to the end is just that move. Because you're not going to do anything else. You're just going to say, hey, this is the move to take. You do this one. There's no reason to evaluate the other ones. This one wins, and if it's the player we want, PL equals player, then it's 1, else it's -1. It's pointless to add up the squares of the other ones, right? What I'm saying is that if you're on this one, if you find this move wins, like you're playing this X here, well, then X wins. You don't go and then evaluate this one and this one because, like, well, no, the X wins. X is going to make this decision. It would be stupid to do something else. So you can cut down on the scoring, and doing something else would actually screw up the scoring because it might do something wrong. And this is kind of not quite a min-max strategy here, but this would be at least one move down you'd see. If the opponent wins, great. Now we have one more consideration here. Game results open. And game result open, what has happened there? This is where recursion gets in, so I'm going to put a return score at the bottom. Score plus equals score to n, so this is where the recursion comes in. And this is our clone board now. We give it a clone board. And now I know how to do the recursion correctly, how to get rid of the first case. So we just do this first. For per player, and now we want to say next player, player. Next player, current player. Be very careful here. Set player, current player, current player. So what we're saying is if it's open and we go to the next level, and this is where we're going to split this off here. I'm going to put this up here so we have that recursive end state. Board.getState. Based on the current state, if it's closed, we do nothing. It's closed, we can just return 0. There is no score here. If it's win, we return the winning player. If it's open, this is the other case. This is where it goes down here. Game open, we do nothing here. Get rid of this mut score down here. And this creates the guard for the entry, so that this main thing here, we don't have to duplicate the logic here. We say get to score, score to end, CB, player, next player. We just add it to the score. Who wins and who loses, then we return the score. Perfect. Now score to end here. That should be enough. Score to end works. Gets a score for every single position. Let's see if this actually compiles. Never will. Of course not. We never make that error. 193. Return if. Okay, that's probably it. So either chat's broken or you guys are quiet again tonight. That's fine. That's fine if you're quiet. But I hope chat's working. Use size 193. PL equals player. What? Local variable. So I think it's just confused there, so let's fix the other errors first. 200. Thanks, Rick Nakas. Verified still working. And score to end. This is just board. Don't get closed mask. $216. Get small. It's just this board.small mask. Score to end is CB. It wants a reference to that for some reason. Let's do this again. Not in this scope. 238 SBX. No, we're just gonna do this. State.random free. 2 if closed and it's not equal to 0. 219. It's not equal to 0. Oh, we get this shit again too. This is just like, yeah, some things use references, some things don't. There's no pattern I can discern to it yet. So it's like syntax overload here. I don't like the fact that lambdas have a different syntax. This is something I actually did in Leaf. I made sure that lambdas and normal functions have the exact same syntax for signatures, because knowing coming from C++, I hate the fact that lambdas have different signatures than normal functions. It's a pain, and C++ is even worse. But so you end up with this stuff where these arrows are just kind of weird. Expected use size. Oh, because this is now a tuple, so we do 0.1. Expected use values found and I32. Oh, because we want 0.0. What's this one? 94. Now this warning actually bugs me here. Iter's assigned to but never used. Yeah, I know I assigned to it, and it's complicated to remove the thing then. So I'm going to ignore that for now. Although we can probably do something like equals iter just to get rid of the error. 206. This has to be a mutt. We love our mutts in Rust. Mutts everywhere. Let's... Oops. Break. Found tuple. Well, that's interesting. I don't believe I changed anything there. Why the hell is it expecting a tuple? Did something else break? Okay, just a random error message I got wrong. So now let's do... We have this new strategy. We think it works. Called strat local. So let's go to play. And let's pit strat local against strat random, first of all. Because if it can't beat strat random, it's pointless. Well, that's bad. That's really bad. It lost the first one. It usually wins. Okay, it's possible random got lucky, right? So it can't always win because random has a chance of actually getting lucky. It does seem to have the tendency to win, though, doesn't it? It has a decent tendency to win. It only lost that first time we ran it. A tie is also okay because you don't lose a ranking to it. Okay, so strat local actually appears to win against strat random. It has a stronger, and this is where I wish we had a loop here, but it takes so long. It appears to win. And we don't really have to debug what the hell get spell move is doing. We're assuming it's working because it's doing well enough. Now let's pit this against strat 1 equals strat Monte Carlo predict new 1. Let's pit this against our Monte Carlo player to see which one is doing better. So player 1 is Monte Carlo, player 0 is the local strategy. 1 wins. Tie game. Not playing out very far. 1 wins. 1 wins. This is not looking good for this idea. 1 wins. Tie game. Alright, so that's not good. Okay, except we made an error. There's something we didn't do yet. Ignoring that, so as it is, Monte Carlo is always going to win. But it's this thing here, random free right here. We don't actually want to do that. We want to do get best small move on and state.big for self.player. We assume it's his turn. Okay, so we're not considering the big board now. So this is the big board now. It also does it. Will that actually make a difference? 1 wins. Just to play 1 wins. It's very slow because it's, you know, doing a lot of calculations. 1 wins. 1 wins. This is not looking good. But it's a confirmation that this approach doesn't work. If we want to see how this actually competes in the thing, we might as well. We'll see. This should put us pretty much last. So let's just play it once and let's submit it and let's see what happens. There's no harm in doing that. We can always go back to the other one. Except we actually have to change the main move. That's way over here. Strat equals box new strat local new state.player. Play it once and watch us. So AI is not a problem to beat. And so this is a strategy where we don't ignore. We actually lost on this one, so that's terrible. Oh, we did make a wrong move. What happened there? Shit, maybe the strategy takes too long for this game. Well, we're not even going to be able to check it. I'm betting it's that first move just takes too long. And... Yeah, that first move probably takes too long to do. Because we output nothing, 4-4. Let's find out how long that's taking. Play to win. Where's this inner instant here? Let n equals standard time. Instant. Now. Took. We'll assume this is always in nanoseconds. That nothing takes so long. Ah, come on. Player. Alright, so player 0 took too long for the first move and for the second move. That's a problem right here. The first and second move took them too long. We'd have to hard code the first move, but the second move, I don't know. And the third move, surprisingly takes just as long, which is really weird. All right, let me take one short break, and then I'll be right back, okay? And we keep looking at this. All right, I'm back. I'm thinking about what we can do with this. It's very long evaluation. You notice it goes down over time until at the very end when there's nothing left. It goes really fast. But player one's always winning anyways, so I don't think we have to worry about optimizing it too much. But it would be kind of nice to see what happens. So the one way we can try, we could optimize this, I don't know how long it takes to calculate, is, not this one, given the state of a tic-tac-toe board, for every position, there are 3 states. It's set, it's not set, or it's empty. So how many states are there to a tic-tac-toe board? There are 19,000 states, which isn't so bad. We could actually calculate. So what? Although this would take forever to calculate, this might be a bit of a problem to calculate. So if one board is taking us almost a second, that would take us 19,000 seconds to calculate. What I'm thinking of is doing a table in the game. On the local strategy, what is the best move? Given a current move, what is the next best move based on the local strategy? And we could use that for the heuristics. Let's see what happens if we do this in release mode. Release mode, and we do target release. Let's see how long these things take then. The Monte Carlo one performs even better then because it has even more evaluations. But what about this small one? That number there is... Okay, so that's only 40 milliseconds. 40 milliseconds? Is this something we could actually do? 0.04. It would take 13 minutes, based on that strategy, to calculate every single outcome so the look would be constant. That's actually within reason. We could calculate everything if we did code to do that and we didn't screw it up. So that means for all, we'd have to find a way to store it though based on the current state. Now, how would we store that too? Because if we use 2 bits per value, we're going to end up having more values, but that's fine. Some of the states don't actually exist. Some states are duplicate, I guess. Alright, so that's an option, but do we want to do this option considering the fact that it doesn't win anyways? But do we need this lookup possibly for the main heuristic? Would it be helpful to say on a mini board, how do we force a win? How do we force a certain win? That might be something helpful to know, just having this output there to begin with. How can we do that though easily? 13-minute turnaround time kind of sucks on release mode if I do it correctly. I'm just thinking. I don't know if I want to do that or not. It'd be kind of a fun experiment, but it might not help us win the game at all. If we could think of some reason why we'd want these values anyways, and again, these values are given for a small board, given any combination of X and O's, tell us what move we should make, what move gives us the best win. But let me check something first. I think before we do this, I want to verify something. I think we have an error. Thinking back to that one where we did strat local against strat random, and strat random won once. That shouldn't be possible. Should it? Oh no, Kang, I'm thinking of the small board. On a small board it wouldn't be local possible. On the big board it would be possible. I don't think it's of value to actually do this calculation now. Because if you think of the big board, yeah, I don't know. Just don't know. So what else do we have to do now? What other heuristic could we possibly do? We can evaluate the board better. I don't think looking at the small board is going to be helpful. We could calculate a lookup table based on that, saying which is the best move for a small table, and that might help the heuristics, though, given a small board. But again, we don't know who plays in the small board next, because in the case of the small boards here, there's no guarantee that it's XO, XO. It could be XXXX. It can completely be dominated by one player because the alternating happens to the rest of the board. So I don't think that's a good approach. So I'm going to leave that for now. I'm not going to do that approach. We're going to look for something else. But I got the refactoring I want to do today, at least. So strat local always loses. Testing strat local. And he can't compete, so let's get rid of him. It can't go fast enough. But now we can actually test locally. We can test locally two players what we want to do. So we make the Monte Carlo strategy, and this is part of the point. We don't have to wait for feedback from the system. We can test things locally on the Monte Carlo one. So Monte Carlo has... What options does it have? It has search depth. So let's do that. Depth. I think this is a use size? I don't know what it is. It's an I-32. Depth. So we can compare different depths. And now, the logic here is, though, you might be thinking, well, obviously, wouldn't a better depth be always better? And the reason why it's not is because of the time factor. The deeper you go, the slower, the less time you have to do. And who calls get best move score? Get best move score is called depth, self.depth. So the deeper you go, the less boards you get to evaluate. And the heuristic then changes. So the heuristic then is basically, well, you know, and the shallower you go, the more moves you evaluate, the more you rely on the heuristic. So this should give us an idea of which one actually performs better, for us at least. There's no guarantee. So now we can do Monte Carlo against Monte Carlo. And we'll give the first one a depth of 30, and the second one a depth of 40. And let's see who wins this more often. Ah, crap, I did commit. I didn't mean to do that. Oh, whatever. And I'm going to build these in release... No, shit. Release mode. Is that fair? No, just do debug mode, because that's the way it's going to play. Because it's time-based. Expected 2 parameters. This was an inch here. We're going to just do 30 for now here as well. And so what we're going to do is we can test locally and figure out what is the best value for depth based on what we have now. Well, as always, we take away that bit of it. Player 1 wins. Player 1 wins. Let's just run a few of these times. Now let's write it down here. 1, 1. 0. And 1 0 1. One. We should encode the starting strategy move. What is the care thing there? So far, a better depth is winning. Just kind of disconcerting. 0. That's 110 of these, so we get a good number. 0. One. So this is obviously something you'd want to do in a loop and run like 1,000 of them. But then we'd have to sit here and wait for 1,000 of them. 0. And this is really close, right? Like, this isn't enough to actually say who wins. And let's do another set of them. 1. Now I can run 8 at a time. How can I do that in Bash? How do I do a loop of 8 in Bash? I keep forgetting the syntax in Bash. Help 4. Loop from 0 to n Bash. Would it actually search find something? Bash for loop examples. I want to do this correctly because I mean I could just keep put it in there for var .n. So for I n 1 .8 do echo $I. Done. Well, that wasn't helpful. There we go. That's more like it. So what I can do here, I'm going to put these in the background. No, it's just going to be weird. I'm going to put these in the background. All right, perfect. Target/play debug/play. One 0 0 1 1. So we could probably output this better, but that gives us 1 0 1 tie 0 1 1 0. It's not like dominating that that one wins. So let's do that again. Zero, zero, 0 1 1 0 1 1. In that case, there wasn't even. All right, so there's no Barney, yeah. Yay, thanks for the cheer. Yeah, Ruz, I don't remember. Alright, so if anybody knows how to do the threading in Rust, that would be helpful right now. Anybody know how to do the threading? This is a good chance for me to learn threading. We want to run this thing several times in parallel. So let's figure out how to do a thread in Rust to make use of my multi-core system. Rust, thread. What is this move stuff? It's not helpful, Barney. But it would certainly thread it. Okay, so I'm going to make a function here. We're going to make a scoring function first. It's going to return a function result. Score 1. And this should return an I-32, who wins the game. And I should put this all inside there. Perf, we don't even need that anymore. Just, perf was part of main. I'll put the comment back there. Okay, so what I'm trying to do here is the scores. Make a function that actually returns a score, and this will return 0. Print line or the win. Play to win, let result. We don't need these for now. Return 0 because it's a closed game. Return player. And score 1 means we're scoring player 1. Who wins? Player equals 0, then we'll return 1. Else we'll return 0. So what this score 1 function is doing is saying for a single game, gives a score of 1 if our player won, 0 if it's a tie, -1 if you lost. And then we'll try to add these up. We'll run them through a job manager, a whole bunch of them, and score them up and see in the end what the result actually is. And this will return 0 as well. So that's all return 0, return 0. So score 1, we have print line player 0 has score 1. Okay, player 0 has 0, so the game tied. That was what the tie means. Player 0 has 1 point. Player 0 has 0 points. Player 0 has 0 points. Okay, so the second one usually wins. Now, what we have to do is just threading stuff here now. Use standard thread. Is this the correct way to do it? If I want to do like a pool of threads, anybody know how to do a pool? Like I want to say like create 100 of these things and use all the cores and just run them? Is there a way to do that? There must be a way to do that, and I just don't know how. Rusted thread pool. What I want to do is I want to run a calculation on a bunch of threads and sum up the results. Who knows how to do that? I want to create a sum up pool, rust pool, sum results or something. What is rayon? That looks complicated. Oh, there it goes. And okay, rayon isn't quite doing what I want. Based on this example, I do want more control over it. And that's a part iter though. Well, maybe rayon is the correct choice. Let's figure out rayon then. How do I use rayon? Crates. How do I do this stuff? I always forget to do rayon. Let's try rayon. And we're going to extern crate rayon. Extern crate rayon. Now this code isn't making it to Steve. In this code we can use the crates. This code is running locally. We'll not be submitting this part of the code to coding game, so we can use all these crates. So we can certainly use rayon here. If rayon's the way to go, and we can try it. And this syntax, now that I see it, probably is okay. And I'm just trying to figure out how to do it. So it repairs sum, and it does a sum, perfect. Yeah, because this is just our local code. So what we can do here is we can say let score equal how do I do a range again? Let's just run 180 of these things first to see what it runs. Dot par iter dot map. I don't care what the index is, because what I'm doing is score 1 dot sum. This is an I32. How many iterations do we have? We're going to say iterations is 8 and score 1. The score is the sum there. Par iter. Okay, so it doesn't like par iter on that, so it must be doing something wrong there. Par iter. Okay. It's probably because of my type here somehow. Can I take maybe this aspect of it? I don't remember. No. Okay, so I can't just call it on a range of stuff here. We can do something stupid like this. Just happy with that. So we did an iter and you got a score of 3. Good. So this is what I want to see. We did that. Let iter equal, let's do 100 of these things. Iter. Iter. Non-constant value. Well, it is a constant value. It's right there. How is this not a constant value? Constant. It's happy with that. All right. Alright, so where's this code? Now they should be using all of my... Alright, so Rayon is... Yes, Rayon's using 600%. I don't know how it decides how many it uses. So this may screw with the streaming. I don't know how many cores it decides to use. Preferably, I'd like to say it should use 6, not all 8, because otherwise it will be competing with OBS. And OBS seems to be taking its fair share, so that should be fine. So I don't know. If anybody knows how to control it, I'd like to limit how many CPUs it uses just in case. And 100, this could take a while. So what do we have? Check the Rayon FAQ. You guys will know when I stop streaming when I turn into a still image. Yes, that's correct. Alright, how do I do this? Rayon num threads. I like this. Global function. I don't see how that tells you number of threads. Well, let's just use the global variable. Okay, so in 100 iterations we got 48. That does not sound convincingly like it won. That seems to be fairly even. Let's convince yourself that this is actually doing something useful. Let's take the first strategy down and say look to 10, 5 ahead. Now clearly strat 1 should win. So it should have a negative score, so let's do it again. Let me check something first. Rayon num... Actually, it's over here. Rayon num... Yeah, it appears to be environment variable is the easiest way for me to do it, but there's probably also a way to set it up in the code it looked like. Okay, so now top over here, it's not using the environment variable. So it totally ignored my environment variable. Did I type it wrong? Rayon num threads. I'll check that afterwards, but it appeared not to use that. Because the top thing... It doesn't show it is running right now, so let's run it one and see. This should be a negative value, so we should have a negative value now for who wins. Come on, come on, come on, come on, come on, come on. Taking its time, taking its time, taking its time. I mean, it has to take its time. And we said 100 milliseconds per move, so it's a fixed amount of time, basically. It can't go any faster. If we compile it in release mode, it's going to take the same time. Except, again, in release mode, we might want to say, hey, look, take only 10 milliseconds. All right, so the score's a lot lower. If you only look 5 ahead, it's only... Oh, wait, this is weird. It's still a positive score, though. That doesn't make sense. Having a positive score makes... It still means it's winning. I got something wrong. Oh, wait, that would mean... I thought my 40... That would mean the 48 from below was actually a massive success. Let me double check this. We have score 1. What does it return? 0. If it went... Ah, shit, this is why. Because this has to return in -1. And that would explain the difference. So the first 48 was pretty much a tie, I guess, probably a bit less. And the second one here was probably a massive loss if it would have done that. But here's Rayon number threads equals 6 as an environment variable, and it ignored it. which is unfortunate. Oh wait, I said 6. All right, let's try 2. Let's try 2. Maybe 6 is going over 100%. And there we go. Yeah, okay, so that works now. 2. Don't know why 6 went over 600%. Maybe just switching overhead, but this will take too long to do this one, so we'll get that rid of that. So now we have a way to compare these things. And now we can compare something like strat local against strat random. We said strat local should work, should always beat random. Maybe not. So let's just put this back to 6 just to make OPS, make sure it has times. And in this case, using a release mode would probably be faster because these are not time-based, but let's just do it this way. Run it once. Well, now it's not going over 600%, so that's a bit weird. Exciting, waiting, no output. Yay! And we're not playing a lot of games, we're playing like 100 matches. But we strongly suspect strat local to win, and we just want to confirm it because I was counting by hand before. But what this setup does is it gives us locally a chance to compare our own strategies at least, how we do against ourselves, so we can test the heuristic to see how much it helps. Now the first thing I want to check here is that starting square 4, 4, and right, this isn't a perfect score. So this is bad news for strat local because it means the score of 51, it means, hey, there's a lot of ties in here and some losses. So strat local isn't that great. Strat local is that was the idea we had from last show. Okay, so what we want to do is we want to do this. Now we want to do the other thing in code is we're going to say 40 and 40, give them both same depth. Or 30 and 30 is what it was before. 30 and 30 same depth. And in the entry we had this special case here. We set up as the first turn, we're going to return 4, 4. Let's put that in the strategy itself now. So the strategy decides to do this. In the Monte Carlo one, Monte Carlo, we want to say, let's do something called first move. And it's going to be a cell. First move is a cell, an optional cell. Option cell. Option use size. And so the get turn is going to be here. Get closed mask. And we're going to check the state of the main board, how we check this, how the closed mask. Something has to tell us it's the first turn without being too expensive. All right, let's just do this one. If is sum and state dot any set and not state any set. If there's nothing set, then we're going to do this. Then we're going to do return No, use size. That'd be use size. Use size. Use size. Use size. Use size. Use size. Turn first move dot unwrap. Now we have to do an is any set function. Is that taking the board? That's taking the board. Board state. Board state has to have an is any set function. Public function is any set. It takes an and self and it returns a bool. Say if big dot get closed mask not equals 0, return false. For I and 0 dot num board num cells. If small self dot small dot get closed mask is not equals 0, return false. This is going to slow us down ever so slightly, but turn true. Or actually just true. Wait, I got this backwards. So it's true, true. This basically detects the first turn. If there's nothing set in the board, what should we do? False, 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 false. Self. Come on, I'm doing typing poorly. So if any of them is set, is anything set in the table or the board? And strategy says basically, look, if it's the first move, if we have somebody specified the first move and there's nothing set, we're just going to perform the first move. So we make this part of the strategy. And this comes up here in new state player, and I'm going to do this sum 4, 4. And these are linear indexes. I'm going to get rid of this here. That 4, 4 is now encoded in it. And what we can do is in the play here, we can say, well, the first player, he's going to take the same thing. He's going to take sum 4, 4. These are cell indexes. This is the middle cell. And the second player is going to take none. So what we can check now is that first move of the center square, does it win more often? Does it help us win more often, or does it make us lose? $39. I don't like languages that end up with like so many braces together. 37, that's all the same thing there. Self.first move. Expected one type argument. Oh yeah, that's like this. Takes a tuple. Get closed. Yeah, okay, I screwed that up. Get I. So again, what we're checking now is that does setting the center square, does it help us win? Apparently in traditional tic-tac-toe, setting one of the corner squares is actually advantageous. We're not clear why, but we actually found the link last time. Somebody gave us the link and said, look, it shows the corner is actually the best chance of winning. And we can compare that now as well. These take a while though, so we did 100 games, and I have 6 threads, and each game could take up to, yeah, 8 to 16 seconds. So up to 100 seconds to finish. Let's say an average of 100 seconds based on dividing by 8 and stuff. Okay. And come on, go, 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 go. There's, like I say, there's no way to speed this up other than actually do. Wow. Player 0 appears to have a slightly increased chance of winning by setting that middle square. I'm not too satisfied this is that great, though. So let's do a none here, just to compare, because none should put us even closer to 0, or actually it's going to tell us what our variance is, because that was so close to 0 is that these two should perform about the same, but the randomness, and this will actually tell us how much we're subject to randomness, and the variance on these things is very different. This little owl is my new toy. It's made by one of my children. It's a cute little owl. He goes with the rabbit. I have these things around my desk. They brighten up the room as opposed to the black speakers. They're like little mascots. So they can come and sneak up on you. Woo! So what we can do is we test other squares. We can test other squares as well. And the other theory was that being in the corner helps. So let's go for the corner squares first. That helps win. It's hard to say. Alright, so this is... This is not really encouraging. This puts our standard variation really, really high. This means this should be 0. Ideally, this should be 0 because both of them have an equal chance of winning. Let's double check the scoring function again. Score 1. There's no oops or licklers, so we play a 0 steps in the initial board game, so we don't set up anything. That's correct. Strat 0, 1, strat your force. There's no force. There's 0, player 0. If it's a closed game, it's 0. It's correct. If player equals 0, it's 1 minus 1. Alright, so I think we're doing this correctly. And that just gives a massive variance. Let's do this in release mode, and they'll both go deeper. If they both go deeper, that should get us closer to a 0. And without getting a score close to 0, it is actually really hard to tell if our changes make a difference. Unless we run more games. Running more games takes a much longer time. Or we can just reduce the timeout. Based on release mode, we can say, hey, look, just take 10 seconds. And that'll at least let our turnaround get higher. Or we can run higher code. That would let us run basically 10 times as many games in debug mode. Yeah, that actually sounds reasonable. So while that's working here, we have the strategy, and there's a time here. There's a time limit specified in milliseconds. And we're going to put that as part of the strategy. And this is going to be, what do they call it in that function? U32. Does Rust have default arguments? Anybody know if it has default arguments? That would be really helpful here. Time ms. Self.time ms. Yeah, so you can see the randomness basically here. It's got closer to 0, but not a lot better. So entry is going to have to be, where's that game created? We're going to give it 90 milliseconds, so the game gives us 100. We're going to put a bit of overhead there, just to make sure. And play, we're going to put it down here as well. We have 10 milliseconds now, because we're doing it in debug mode. 10 milliseconds, 10 milliseconds. And let's put the game count up to 1,000, so we get a lot more of these run and release mode. Now I should actually divide it by what's the average score here. That would actually be better. To normalize the value, score as F64 divided by iter as F64. And this gives us basically our rate or percentage here. Let's do a percentage. Well, no, it's not a percentage, it's a base score. Plus or minus, that's fine. But it won't run this time, obviously. So now we're doing 1,000 iterations in equivalent games, and we're expecting that the value to be very close to zero, the normalized value, because they have the equal chance of winning. Except strat 0, we assume that player 1 has an increased chance of winning, so we have to consider that, how much advantage there is to it being player 0 winning. But that shouldn't make a huge difference. Looking like the game itself, based on the leaderboard. Alright, so here we have 62. This is divided by 1,000. This is a very minor difference. Player 0 has a 6% chance of winning over player 1, which is insignificant. So now let's do this. Let's do sum, and let's stick it in the corner now. Cell 0, 0. And try to play there. Does this actually give us a chance of winning? And we have to see some variation, otherwise it may not be worth it. But the other players we saw definitely go in the middle. But it only makes sense to go in the middle is if you can follow through on that strategy. And now I'm just wondering how we follow through. Is that we might want to check for every small board if it's open to go in the middle. That's an option, or every small board to go in the corner. And that's where heuristics come into play. So what we can do is do a strategy wrapper that wraps two together and says, look, in this mode do this, and in this mode do this. So you can have an overlying strategy that combines two other ones. So you have like a fixed mode one and a back-end mode. And this is what you have in a lot of games when you have games with opening moves. I think some of the initial chess engines do that. They have heuristics for the opening moves. They just look through a lookup of classic games, and they take Grandmaster games, and they say, look, well, this is the first move, this is the first move. And it saves the calculations when you have too many and you have an open board. And we can do the same thing. Let's just see how this works first, though. Well, we need to see a strong indication that this is working. And yeah, this is very interesting. This variation here is that well, that seems significant. I mean, it's enough of a difference. So 0.106, that's enough of a difference to make me wonder if that's valuable. We'll compare this to 4-4 again. Because we're now playing 1,000 games in this strategy. And there's still some randomness, but 1,000 games isn't nothing anymore. It's significant enough that... But it's significant enough that it makes sense that you can use the results. What's interesting though is strat 0 always has an advantage, so it looks like player 0 actually has an advantage in the game. Which makes a lot of sense. If it's like traditional tic-tac-toe, the first player basically gets to decide, does he want to lose or does he want to tie the game? He can't win. You can only force a tie, I think, in tic-tac-toe. Assuming the other player plays optimally. But this is good. We can compare this, and unlike coding games, submitting it is... I know we're competing against yourself, but it's good to compete against yourself because at least we have some idea if we're getting better, and we have ideas of how the other strategies work. And as long as we keep doing better than ourselves, we should do okay. Doing this scoring type approach, because the scoring type approach is, you know, a kind of a fallback. We know it's going to work. And what we could actually do is we could actually compare against a Monte Carlo guy. Okay, so I mean, it's hard to say. There's still randomness involved here, but it looks like this is actually somehow of value. Right, we can make strategy 2 just stronger by giving it more time. That's another option. And that's a way, and this is why Monte Carlo Predict is actually pretty good, is because we actually know if we actually want to compete against a hard player and we don't know how to make a hard one, we can rely on the fact that locally I have a lot more time to deal with, and I can simply increase the depth and the amount of time it gets, and that makes our player harder. It's simple enough, and we know it makes it harder because Monte Carlo gets just better that way. And, right, like if we just give this one 20 milliseconds, ideally, they should win a lot more often. Unless the first player advantage is massive, but I can't imagine that. I can't imagine it's massive. And we took the sum 0-0, but this would be enough to submit. We can say, hey, look, 0-0 seems to have actually an improved win rate over non-0-0. So over an entry, we can do this. We can say, hey, look, 0-0 seemed to be a better case of winning. So we're actually going to do that. And it gets 90 milliseconds. We could up this to 95, but let's just play with 90. It can't make a huge difference. If we're looking for a minor little blip, we could put up to 95 and take our chances. So the next thing we can play with are the heuristics, so the wrapping thing. What else we do? The predict state. We can actually now play with predict state and say, well, what other options do we have for predict state? We can say a different prediction algorithm and see if it actually performs better with a different prediction algorithm. Yeah, this takes a while to perform though, because of the way these things are performing. It just takes a long time. Plus, we're playing 1,000 games, and right, this is probably my CPU might be getting warm. It's not. My fan's working wonderfully. I can hear it though. So we're running basically at 700% for a long time now. So that's 7 cores of the CPU being used continuously, running only at 66 degrees, which is nice. Fans, I can hear it. It's only 13 RPM. Okay, so look at this. Yes, clearly, by increasing the depth, player 0 is clearly stronger. No problem about it. It definitely wins more. And so that's clear, is that to keep it stronger. So we have that, but let's do it that way. We said player 0-0. Playing 0-0 is actually slightly stronger. So we're going to submit that one. We're going to submit 0-0 and see if it actually gets us any higher in the rank significantly. Where am I? Let's play it once and then let's submit it. And let's play 0-0 against 4-4 to see who wins. But again, we can't. It's harder to detect the starting position, so let's just play this. Submit that. And we'll see where it goes. So let's pit it against that. Let's go, where are we? Let's do against some 4-4. Again, this is center-center. Let's see who wins in center-center. 0-0, so a fixed starting spots. And oops, that's not what I wanted. Zero may still have a bias, but that's okay. Ideally, Monte Carlo, if it was run through, would have a fixed starting spot anyways. The fact that fixing it this way indicates we don't have enough depth in Monte Carlo to pick an initial starting position. Let's let all this stuff run now. Oh, I lost my chat window. And where are we now on the leaderboard? Are we going up? We're going down? We're going nowhere? Going down. Well, that's pretty bad. Apparently it doesn't like us now. Alright, it could just be the first initial games, though. Because it's a small ladder and there's some guys that are a lot better than us, we might just be playing half the guys that are better than us. So, and we weren't very high up to begin with. Rank 42 out of 51. So let's see where we are. Okay. Interesting. Look at this. A score of 18. So this is a significant. This is an 18% advantage. If the other player is fixed at 4-4 and I fixed at 0-0, it's a massive advantage. Let's make sure that's... Okay, but yeah, that's stupid because this is this second player, I'll never get to choose that. They'll never get that first game. Alright, but it looks like 0-0 has an advantage. I'm convinced of this now. This one doesn't make a difference here. So putting it 0-0 gives it an advantage. Let's put it down to 10 search depth and see how much we lose. That ranking count doesn't work on that score anymore. So somehow we ended up at the bottom to start with. That's kind of unfair. And we're doing enough. We're not losing. We're winning enough that we shouldn't be in the very bottom. That was just the initial matchups got us screwed. So we can work on heuristics. This is a big deal then. Either we improve scoring or we sort of hard code some strategy, or we go back to the idea of thinking, well, is there some way to combine this strat local? Like when we have the big board, when we have a big board decision, should we maybe use strat local? And we have a small board decision, then just open it up and figure out what to do there? What one should we actually do? Or if there's a first move, should we apply this to every single one of the small boards? And this is where I don't like doing the manual heuristics here, because the manual heuristics are kind of like, well, it doesn't give you a chance. And okay, so but this here we clearly verified. Setting this down to 10, lowering the search depth and relying more on heuristics is not as good. So let's go the other direction. If we increase the depth and rely less on heuristics, do we do better? Again, we're leaving the time constant, so we're not getting more iterations. If I increase this, we know for sure we do better. So the board got a bit longer, and we're still going up. And again, these numbers are very close to each other, so we don't have to go up very high to get back to where we were. What we want to see is if we were at 42, and it was 42 out of 51, and there's now 56 people, if we get back to 42, we assume we're better. If we got into the 30s, we're definitely better. But not enough to be like super excited about it. And I'm going to play with the search depth thing here a little bit first to see which one is better there. And if we're just waiting, and then we'll play with the heuristics function, the predict state function. To predict state function, then we can figure out, okay, who's going to actually win. And we know we can improve that. because we're just counting up bits right now. There's not a good bit strategy there. So 104, so 40 depth, we were at 106, and this is a variance level. We just don't know. The smaller the number we have there, the better, because the smaller the number we have for the depth, it means we get more iterations. And the more we can improve the heuristic, the smaller we can make that number. And that's definitely helpful because the more iterations we do, the stronger the Monte Carlo is. But that means getting a better heuristic. And our heuristic now is quickly and shoddily put together, so it might not be that great. I think I'm only going to go a bit longer today. I've done this quite a while, but we have our code all set up for this evaluation to actually start looking at heuristic, and we're not doing so well. It's really hard to say if it's because, given the randomness in these boards, it's really hard to say how we're doing. If we had a clear strategy improvement, we would make it up. But we don't have a clear strategy improvement. We have minor strategy improvements. We need like a big boost. We need a boost to say like, hey, look, we don't want a score of 10% better. We want to score 100% better than ourselves, so we always beat ourselves. That would be significant. At least we're set up for then tomorrow, though, at least, because tomorrow we can actually work on the individual bits. And we have, like I say, the key thing we did today. Okay, so this is very interesting. Going down to 20 is bad. 20 hurt us a lot, but 30 was okay. 40 didn't buy us anything, so 30 seems okay. And, of course, if we had even lots of time, you'd fine-tune it and say, well, is it 25? Is it 26? Is it 27? And that can make a big difference. Now, let me commit all this. So this stuff seems to be working. What do we say? Main was we have 30, and we started 0, 0, and that was giving us an advantage. So, git commit strategy setup. Now for curiosity, let's compare, just to make sure, one that always goes directly to the end. And 90 here is right to the end because there's only a total of 81 moves in the game, so 90 guarantees you go right to the end. And what we're seeing so far is increasing this number doesn't help you win. Because of the spread out, the heuristic is having more importance than the depth, unless you go down too low. And this is where we can actually try our play to end as well. Like right now, our play to end. Yeah, it's hard to say. It's hard to say how you optimize that. So what we have in state is predict states. Let's look over that again. And this is the small board predict state. How we predict who wins the small state is, if there is a winner, it's that winner. That's very clear, right? Otherwise, we count the number of positions held by 0, number of positions held by 1, and we just say who wins. Who has the most dots? There are definitely some forms here that are more advantageous than other ones, though, and it's a matter of checking which forms they have. But again, in big super tic-tac-toe, we don't know. But they say this is the something we have, we can modify. Is that, well, what is the chance? That do the positions actually count? Does the prediction based on where the dots are? But again, everything, you can't make this too complex, because if you make it too complex and it slows it down, you end up losing as well. Now, what did I check now? Okay. Now, this is very interesting, is that by giving the second one a 90 depth, it lowers our score a lot, or actually a little bit. And what this really points down to is that in our strategy, going first has a huge advantage. That's like just totally unfair if you evaluate the search. So going first is winning us more than anything. Okay. Let's go to the next predict state. What else do we have? Small board. We check the player wins, predict state, and we count up who wins. Now, we had this one heuristic before that said, look, if somebody has that middle section, they have a better chance of winning on the big board. So let's actually add that back in. We increase the chance to 3. Again, 4 is the middle cell. And this is a really, really rough one. Well, let's see if it actually helps. Oh, wait, but they both use it then. Oh, crap. I'm going to get it to Swixley Fitch. Play to end predict state, and let's just do it. Where is it now? Play to end. Well, this makes it hard to actually detect it that way. Whether we ideally we'd have a heuristic as well. So like the strategy function, we'd have a heuristic function. Yay, 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 yay. All right, I'm getting tired. I think I'm going to do that tomorrow, but let's do that tomorrow. Heuristic traits, so that we can plug in different heuristics as well, and that'll let us evaluate the exact same way we're doing the strategies. We combine them with heuristics, and then we can say, given this heuristic, who wins and who doesn't win, and then we can fine-tune it for who does that, and get random. And play to end here, we have to decide if we improve that as well. If it's just Monte Carlo, or people just take random moves back and forth into Monte Carlo, or we reduce the depths and we do the other opponents first, what their best move is, our best move. But I think I'm going to leave this for now where it is, and let's see where we actually made it up to. So we kind of fell down. I don't think it's... And this is where it's really tough, is that playing 0-0 against our strategy is an improvement, but against other people may not be. But we're not making a big difference either way, so we're just going to leave this. We leave this for now, and then tomorrow night I should be back, and we can do the heuristic thing, the plug-in heuristic. And all of this is just to set up to figure out what we can play with and how we can improve this. It's not actually helping us get a better strategy, but it lets us look at things more as how we do it. Is that these guys at the top here, I'm going to score 16, 33. This is a massive deviation. So whatever recurse is doing is a massive deviation from what we're doing. And we know that they can evaluate deeper. And we just saw that too in my examples. Is letting my Monte Carlo, giving it twice as much time, helps a lot. And C++, if he forces optimized mode on, it can definitely help him. But there's other people up here too. There's one Java guy, and I don't think you can force optimization on here. So he's clearly got a strategy that doesn't require like a lot of iterations. I mean, it probably still does, but not as many. And the next guy down is C# quite far, but that's quite a drop down to C#. But you notice at the top here, and okay, so we have no excuse against the PHP guy, because there's absolutely no way he's doing more iterations than us. But like I said, we're pretty close, and we may be going up. So actually, we are slowly going up, and But we have to find some strategy. Just raw Monte Carlo is not enough. The heuristic looks like it's vitally important. Performance optimizations, we can't rely on them. And otherwise, it's hard-coded strategies and maybe tables. That let local strategy that we tried, we confirmed it doesn't actually win, but it hints at something. If we can actually store the table state for each one, given each table state, which one would we want to win? And this is another approach to looking at it. Instead of just playing randomly looking for the wins, you can actually take each board state and say, well, where do I want to play? Which to win this board, which position is advantageous in the main board? And then you look at the small state and say, well, how do I play it to win that small state? And then focus it that way, focusing on winning that. It's hard to, but we'll see when we get there. And so we'll probably drift back up to 42. I'd like to see, it looks like we're already back at the same place we were. If we drift a little bit higher, then we'd know that the 0-0 is slightly helpful. But we know that a recurse last time we checked was always doing the middle. But I think I'm going to leave it here tonight. So thanks for watching. Sorry I wasn't here last night, but I should be here tomorrow night. And if not, then Sunday night. And I'll keep doing more. We'll clean it up. We have some better Rust code. We got to use Rayon, which is great. We did some actual threading work. We're abusing my CPUs a bit, and that's great. And it was super easy. I must say it was super easy to use Rayon and set that summing up function the way I wanted. That was a breeze. I love that, and I'll be happy to use that again. And there's not much news, but thank you very much for watching. I hope you had fun, and I'll be back tomorrow night then. Thank you very much.